But creating this multiply-add process is only half the story for hidden layers. For neural networks to achieve their maximum predictive power, we must apply something called an activation function in the hidden layers. An activation function allows the model to capture non-linearities. Non-linearities, as shown on the right here, capture patterns like how going from one child to 2 children may impact your banking transactions differently than going from 3 children to 4 children. We have examples of linear functions, straight lines, on the left, and nonlinear functions on the right. If the relationships in the data aren't straight line relationships, we'll need an activation function that captures nonlinearities. An activation function is something applied to the value coming into a node, which then transforms it into a value stored in that node or the node output. Let's go back to the previous diagram. The top hidden node previously had a value of 5. For a long time, an S-shaped function called tanh was a popular activation function. If we use the tanh activation function, this node's value would be tanh of 5, which is very close to 1. Today, the standard in both industry and research applications is something called the ReLU, or Rectified Linear Activation Function. That's depicted here. Though it has 2 linear pieces, it's surprisingly powerful when composed together through multiple successive hidden layers, which you will see soon. The code that incorporates activation functions is shown here. It is the same code you saw previously, but we've distinguished the input from the output in each node, which is shown in these lines. And then again here, we've applied the tanh function to convert the input to the output. That gives us a prediction of 1.2 transactions. In the exercise, you will use the rectified linear activation function, or ReLU, in your network.